Welcome to Foundations of Kubernetes. Kubernetes is an automated system that manages the container lifecycle end-to-end. It handles the deployment, scaling, networking, and scheduling of your applications all on one platform. Here, we're going to be running Kubernetes locally using kind. To create the local kind cluster, run the following: kind, create cluster, name of cluster. Running that, assuming you have kind installed, will create your local Kubernetes cluster. We'll also be using a tool to interact with the cluster called kubectl. Kubectl is a CLI tool that is used to interact with the Kubernetes API to perform cluster management and application management activities. So let's get back to the pod. The smallest unit of compute within Kubernetes is the pod. They contain one or more logically related containers that share networking and storage. So to define a pod, we have our API version up here, kind, which is the actual resource. In this case, it'll be pod. Metadata. Inside of that, we have the namespace. You might say, what is a namespace? Namespaces in Kubernetes allow you to logically separate your workloads, configuration, and RBAC roles under a common name. Think of it as a partition or space within a cluster that you can bundle together all the resources for your application that you want to run. We have the name of the pod, and then we have two pieces of metadata: annotations and labels. Why both? Labels are metadata for Kubernetes to make a decision on. Annotations are metadata for humans and tools. Underneath here, we have the pod specification. We see a service account name. A service account is a pod's identity for authenticating to the Kubernetes API. Permissions are bound to the service account via role bindings, which determine the access level granted to the token mounted in the pod at startup. Here, we have our node selector. That ties back into the labels I mentioned earlier. Nodes are another resource within the Kubernetes cluster. This is a single node cluster because it's running locally. And we can use the labels on nodes to influence where the pod will run. Here, since it's a single node cluster, we can't do any kind of advanced scheduling, but I'm specifying a label for this example. And then we have our containers. So we have the container name, the image name we're going to be running, the command that we want to run within the container, as well as the argument to pass to it. We have environment variables that we're specifying, and then we have resources. We have the resources set for our container. Here, we have our requested resources, which are the resources that are going to be guaranteed for our container within the pod. We are asking for 50 millicores, which is thousandths of a core. We're asking for 50 megabytes of memory, and then we see our limits have the exact same values. Generally, you would set your limits to be above what you're requesting so that you can have some space to expand into. But there are cases where you'd set the limits as well as the request equal to the same value. Thing to know is that as you approach the limit for CPU, your container CPU usage will be throttled back down to 50. For memory, your container, if it exceeds the memory limit, may be terminated. If that happens many times in a row, that'll lead to a crash loop back off. Now, as you see, I have resources specified underneath the container. I can have multiple containers within a pod, and the total requests of both CPU and memory for the pod itself will be the sum of the requested CPU and memory per container. However, the limits are enforced at a container by container basis within the pod. Finally, when you specify resources on your containers, it will influence how the pod is scheduled. When you don't have any resources set, the pod can fit into whatever is open on the node. However, when you're specifying CPU and memory, you are now requiring that whatever node that the pod lands on has at least 50 M of CPU and 50 megabytes of memory. Here we have our service count, we have our annotation, the name of the service count, what namespace it'll be created in. Note that it needs to be the same namespace that the pod's in, as well as the labels on it. If we want to get a preview of what the service account will look like when created, we can run. And here we can see what the service account will look like before it's created. Very similar to a Terraform plan, if you're familiar with that. Let's apply it. And then we can use the get command to get our service count and see that it's been created. Now we can run apply against our pod. And we see that our pod is running. If we wait a few seconds, we can check the log. And the pod name. And we see hello, which is what we'd expect from the script that we passed to the container. We can also run kubectl describe pod to verify that our environment variable has been set on the pod that we created. And we see here in our pod specification for this specific container environment, my key equals key. So now, what else can we do with this? Well, earlier I mentioned service accounts. We can bind permissions to those service accounts via roles. So let's take a look at that. Here, we have two pieces. We have the role and we have role bindings. On the role itself, we could specify metadata once again, label, annotation, name, and then we have a rule section. Here, we define what API group we're going to be using, the resource within that API group, and the verbs. In this case, get, watch, and list. And then we have our role binding. This attaches the role to our specific service account. So we see that we have role ref with our kind role, name, test role, and the API groups being specified. We then have in our subject, our service account with our service account name, as well as the API group specified. And then we also have our labels and annotations, as well as the name of the role binding. Let's apply it. I'd already created the role. We've configured the role binding. We can see that our pod is still running. Let us use this other great command, kubectl exec it, put in the pod name, double line, specify that we want to shell in, and we're inside of the pod. And from here, what we can do is take advantage of the permissions that we have just passed to the service account. So I had given the permission to get pods within this namespace. So let us see if that works. And there we go. We're now able to get pods. Now, if I tried to get something else, like for instance, notes, we see that we can't because there isn't a permission defined on our service account within Kubernetes that allows us to perform this action. Now, let's take a look at another feature that we can use with pods. Let's introduce Init Containers. This is a container that'll run before our main container down here will kick off. We can use this to do some pre-configuration, to set up some files, to run a script. In this case, we're just going to be creating this dummy file. We'll also introduce this new component as well, volumes. Now, this is an emptyDir volume whose lifecycle is tied to the lifecycle of the pod. So when the pod gets deleted, the data here gets flushed out. The data in the emptyDir is written directly to the node disk. Here, we're using this emptyDir volume to pass a file from our init container to our main container. So here we have our volume defined. Then we mount the volume at a specific path, my config, and later we see it being referenced down here. So let's give it a try. We will apply the new one. Check out our pod. Cool. We can exec into it. ls, we see the folder myconfig, and we see our file as present, file.txt. What happens if we delete a pod? Let's take a look at that. Notice the pod's now gone. It hasn't been restarted. There is a mechanism within Kubernetes to solve for this, and that will be the topic of the next video. Thank you. Have a great day. Please like and subscribe.